Okay guys, in this last example of a work through polynomial inequality, we're going to take a look at an example where you don't necessarily have a zero on one side and you're dealing with rational functions, so it's kind of a double whammy. So the very first thing we always want to be doing with these polynomial inequalities is getting a zero on one side. So I am actually inclined to add 2 over x plus 1 to each side, or in other words, just stash this back on the left side. So what we end up with, first of all, is just this expression 1 over x minus 3 plus 2 over x plus 1, and this is going to be greater than 0. Now, before we can actually proceed with finding our critical values here, which, by the way, remember, occur at the zeros of the top and the bottom of your fractions here, the thing is that's a little bit difficult to do when you don't have a single fraction. So what we're going to have to do is find a common denominator first, and we're going to have to add these two fractions together. So as far as my least common denominator goes, I would recognize that really x minus 3 times x plus 1 would be a good least common denominator. So what I'm going to do is I'm actually going to take each of these expressions and I'm going to multiply the top and the bottom by the factor that I need to multiply it by in order to gain a common denominator here. So x minus 3 over here on top and bottom. And so what we end up with is this. Now, over x plus 1, x minus 3, x plus 1, x minus 3, I would get, distributing here, I would get x plus 1. And this is all plus now. This is also over x plus 1, x minus 3, which is kind of a cool thing. That's what we wanted. And on top, I'm going to get 2x minus 6. So when it comes down to it, what we're going to do now is we're essentially just going to write one big ratio here, x plus 1, x minus 3. And on top, we're going to combine like terms, we'll add our numerator. So we say x plus 2x is 3x, and 1 plus a negative 6 is a negative 5, and this is greater than 0. So here we are. As a matter of fact, we went through all that work just to get to a good starting point, but I would start by just factoring the top and the bottom if at all possible. And I noticed that the bottom's already factored, and I noticed that the top is unfactorable other than a GCF of 1. So from here, let's go ahead and get this party started. We say, well, then what are my critical values? Now recall that your critical values occur at the zeros of the top and the bottom of this expression, because the zeros of the top are the zeros of this entire rational function, and the zeros of the bottom are the vertical asymptotes of this function. So when we say, what are my critical values? Essentially, we're going to say that we get one at negative 1 and positive 3, because that's where our vertical asymptotes lie. And if I were to set 3x minus 5 equal to 0 and solve it, we would get x equals 5 thirds. So I'm going to throw that on my list also, 5 thirds, and I'll put a box around this. So from here, as we typically do, let's go ahead and get our graph set up so that we can set up our test intervals. Now I notice that I have 1 negative and 2 positive critical values here. So we're going to go, let's see, negative 1 would be right here. Suppose we say 1, 2, 3. So 3 would be right here, and 5 thirds, that's 1 and 2 thirds. So I'm going to say that that's right here, 5 thirds. So our three critical values are these ones that we have listed here. Let me actually, a little bit easier to see if we switch our color. How about a blue? So we would say that this is a critical value, this is a critical value, and this is a critical value to split up our number line. We'll go with a lighter shade. A little better. So our test intervals, let's go ahead and get these set up here. So test intervals. Because we have three critical values, then we're going to have 4 intervals. So these intervals are from negative infinity up to our first critical value, negative 1. Our next test interval would be from negative 1 and going up to 5 thirds. Our next test interval would be starting at 5 thirds going up to 3. And then our last test interval is going to be 3 to infinity. So as we do, let's go ahead and designate some x values from within each test interval to go test. So for instance, here to the left of negative 1, I'm going to test negative 2. Between negative 1 and 5 thirds, we guarantee we have to get 0. That's easy to test. 5 thirds to 3. 5 thirds is 1 third less than 6 thirds, which is 2. So we could say that 2 is between 5 thirds and 3. And then to the right of 3, we'll just pick 4. And recall that what we want to do is we want to plug all these back into our original factored expression, which I'm going to point this out to you as bing, this guy right here. So now this isn't going to be as fun to plug things in, but recall that we're plugging it into the factored expression, which really only we're trying to do this. We're trying to figure out, do I get a positive or a negative on this expression on the left? So testing this out, we say 3 times negative 2 minus 5, and this is all over negative 2 plus 1, negative 2 minus 3. And we're claiming that this is greater than 0, according to the original expression right here. So let's test this out. I get 3 times negative 2 is negative 6, and negative 6 minus 5 is a negative 11. And then in the denominator, what I get here is I get a negative 1 times a negative 5. And so let's assess the situation. Down here, this is all a positive. I get negative 11 over a positive 5 is greater than or equal, greater than 0. But see, that would be false because a negative cannot be greater than 0. So what that means is I'm going to toss out this interval right here because it couldn't be a possible solution interval. Now testing 0, again, we're going to say 3 times 0 minus 5, and this is all over 0 plus 1, 0 minus 3. This is greater than 0. So on top I get a negative 5. This time on bottom I get a 1 times a negative 3. So a neat thing happens on the bottom. This is all a negative. So I end up with a negative 5 over a negative 3, which tells me that this is a positive, regardless of what it is. And a positive is greater than 0. So this means I get excited. This is part of my solution interval here. Let's keep going. So we'll test 2. 3 times 2 minus 5 all over 2 plus 1, 2 minus 3 is greater than 0. So we would get 6 minus 5 all over 2 plus 1 times 2 minus 3. And so what we get is this. Suppose we would get a positive over a negative, which would not be greater than 0. So this is false. And again, we would reject this as a solution interval. And then we would say testing 4, we'd say 3 times 4 minus 5. And this is all over 4 plus 1, 4 minus 3. Let's see if this is greater than 0. So we get 12 minus 5 on top, so 7. And then on the bottom here, I get a 5, a positive 5 times, I suppose this would be a positive 1. So neat, we're taking positives divided by positives. I know that I get a positive, and a positive is greater than 0. So again, I'm going to accept this as one of my solution intervals here. So let's do this. Let's go ahead and write down our solutions in this case. And it's going to play a really big role here, the fact that this was just a greater than. Because it is greater than and not greater than or equal to, and that means that we're going to not include any of our endpoints on this entire thing, excuse me, even if it was a 0 like 5/3 in the first place. Now if this had been a greater than or equal to 0, then we would have to include 5/3 on this interval right here because 5/3 would make it 0, which is greater than or equal to 0. But again, because it's not greater than or equal to, we're just going to say that our intervals include parentheses around them. We're not going to include any of their endpoints, and here are our solution intervals right here. And if we're going to make a sketch of this, we would just say parenthesis at 3 and to the right, so 3 to infinity. And our other interval was between negative 1 and positive 5/3. So here is our graph of our solution interval. And these are actual solutions. Cheers.